Hi, it's Mr. Mac, and in the third of our series, Maths Skills You Need, we are going to be graphing linear relationships. So we'll be taking real-world examples of linear relationships and putting them on the XY plane.
This is Mr. Mac. He can explain things really well and is a lot of fun to watch. You can subscribe to Mr. Mac's Physics channel. You will find mathematics problems, science demonstrations, astronomy and space pics, physics calculations and simple explanations of advanced concepts.
So we'll be graphing linear relationships. As you can see, here is a picture of a Qantas 747 at Sydney Airport. One of the questions we'll deal with has the cruising speed of a passenger airliner. What we're learning to do is to model linear relationships graphically on the XY plane, and we'll be able to construct and analyse linear models using features of straight line graphs. And here's worked example 1 about direct variation. A Qantas A380 is a large wide-bodied airliner that was developed and produced by Airbus. It's the world's largest passenger airliner. This plane has a cruising speed of 1,050 kilometres per hour. And the distance from Sydney to Los Angeles is 12,047 kilometres. Part A, the question is there a direct variation relationship between the distance travelled and the time it takes? If there is, determine the relationship. Now we must be careful to answer the question that's actually being asked. So firstly, let D be the distance travelled and T be the time taken. Well, 1,050 kilometres takes 1 hour. That's what the cruising speed means. If we add on another 1,050, we get 2,100 kilometres, and that takes 2 hours. Add on another 1,050 to get 3,150 kilometres. That takes 3 hours. So the distance is increasing 1,050 kilometres every 1 hour. This means that there is a direct variation relationship of distance and time. And we can write that as D equals 1050 T. Part B. Well, firstly, two quantities vary directly or are directly proportional if one quantity is a constant multiple of another quantity. And what we need to do is to use that relationship we just found, D equals 1050 T, to complete the table of values and then plot a graph. Well, here's the table that's given. It's got the heading distance travelled on an A380 versus the time taken. And you can see the horizontal first row is the T values from 1 to 12. And we've been given D values of 1,050, 2,100, 3,150. So let's work out the next value. To do that, we simply add on 1,050. And we can do that on the calculator, and we can see that the answer is 4,200. Now, if we press equals again, we don't have to keep adding 1,050, add 1,050, add 1,050. We can just press equals because most modern calculators has a constant adding function. So just by pressing equals again, we get all the other values. So here they are. And you can write those in and fill those in just by pausing the video. Well, what about the graph? With a graph, make sure you put a title. The title of the table becomes then the title of the graph. We'll then put in straight lines, rule them with arrows at each end from an axis, and put in even marks all the way along. Usually it's a centimetre apart. And we do it both across the horizontal and up the vertical. And then we number them and label them with a name and include units in brackets. So the horizontal axis and the vertical axis are now numbered, labelled, and have units. And then we use crosses for points. This is a far more accurate way of showing the exact point. And you can see there I put a line at the point where the cross is at time 10 hours. And then finally we rule a line of best fit. Now for this set of points, the line will go from 0, 0 through every single cross. And we've done the graph. For worked example 2, we're going to use a different graph, one that's been given to us. Los Angeles is in the USA, of course, where they measure temperature in degrees Fahrenheit. And if you go there, you'll need to convert degrees Fahrenheit to degrees Celsius. So look at the graph, and the question is, what is the gradient of the line? Now I've just put the initials down the side there, TANLUCR, just to remind you of those steps in making the graph. You might just have a look at this graph and see that it ticks all those that the graph has: title, has axes, has numbers, labels, units, has crosses, and it has a ruled straight line. Well, we're not given crosses in this because we're given simply the straight line. Now we can read 2 points from the graph to the nearest number. One of them is here circled right on the vertical axis, and that's the y-intercept 0, 30. And here's the other one, again it's circled at the point 50, 120. And from those we can find the gradient. The gradient is given the symbol m, and it can be found by m equals rise over run. Now the rise is how far it goes up vertically, and the run is how far it goes horizontally. So we look at the numbers, and the 120 is the highest number on the vertical axis, and the 30 is the lowest number that's circled. And the run we find by going from 0 to 50, so it's simply 50 take away 0. When we do that, we get 90 over 50, or simply 9/5. And that's the gradient of this straight line. B, is this an example of direct variation, as we saw in worked example 1? And justify your answer. Well, no, it's not. For direct variation, it must be a straight line graph and pass through 0, 0, the origin. This graph has a y-intercept of 30 or thereabouts. So it's not direct variation, even though it is linear. So it's a linear relationship with a straight line, but are not direct variation. And you can see this on the graph here. Well, let's have a look at part C. It says, use the graph to convert 25 degrees Celsius to Fahrenheit. Well, let's find that on the graph. So we look along the horizontal axis and look for the circle, and we circle it on the straight line above the 25. And if you look on the horizontal, the y-axis, you can see it's around about 75 degrees Fahrenheit. So 25 degrees Celsius equals 75 degrees Fahrenheit. Part D, use the graph to convert 100 degrees Fahrenheit to Celsius. Again, we're going to circle a point on the line, but this time it's going to be next to the 100 degrees Fahrenheit. As the circle is there, and the circle is on the straight line. It's along from the 100 degrees Fahrenheit. And then we look at that circle and say it is above the 40 degrees Celsius on the x-axis. So 100 degrees Fahrenheit equals 40 degrees Celsius. Well, let's have a look at part E. It says, now check your results for C and D by using the formula F equals 9/5 C plus 32. This is a linear relationship. For part C, we're going to substitute C equals 25. Remember, we were given 25 degrees Celsius. So we simply substitute F equals 9/5 times, instead of C, we write 25 plus 32. And we can calculate that If you look at the first term, it should be fairly easy to see how 5 goes into 25 5 times. So 9 times 5 is 45. 45 plus 32 is 77. But when in doubt, use a calculator. F equals 77, which is actually more accurate than the 75 degrees Fahrenheit that we found graphically. Let's check part D. This time we're going to use F equals 100. So we replace the F with 100. 100 equals 9/5 times C plus 32. Now we need to do a bit of rearranging. So we take 32 from both sides. So 100 minus 32 equals 9/5 C. And then 100 minus 32 is 68. Then we want to divide by 9/5. When we divide by 9/5 on the right-hand side, we're just left with C. When we divide by 9/5 on the left-hand side, it's the same as multiplying by its reciprocal. In other words, we multiply by 5 on 9 instead of 9/5. And when we do that, we need a calculator. It turns out to be 37.8, correct to 1 decimal place, which again is more accurate than the 40 degrees Fahrenheit that we found graphically. And so when we've got a graph, and it's a fairly small one, we can see that the calculation is more accurate if we use a formula. But of course, if we made a bigger graph, we'd find it more accurately. So we've been graphing linear relationships by drawing up straight axes with linear scales labelled with units, and then plotting the points, drawing a line of best fit, and then looking at calculations for the gradient, looking at the y-intercept, and then applying it back to the real world. I'm Mr. Mac. Thanks for watching.